Welcome to the Explainer. Today, we're going to trace the incredible journey of a cryptocurrency transaction, all the way from your wallet to a confirmed block on the chain.
So, you click Send. It feels like it happens in an instant, right? But behind that one single click is this amazing, multi-stage process that makes sure your transaction is not only secure, but completely permanent. Okay, let's dive in and follow the data.
We're going to follow the life of this transaction through 5 key stages. First, how it's born. Then, where it waits. We'll look at the puzzle miners have to solve, how the whole network agrees on the solution, and finally, how it gets confirmed on the blockchain for good.
All right, first up, stage 1. So how is a transaction actually born? Where does it all begin?
Well, it all starts with you, in your wallet. When you authorize a payment, your wallet creates and signs this digital message. Now, for those of you who work with databases, you can think of this as basically initiating a write request. It's an instruction that's just waiting to be processed.
So once your wallet broadcasts this request, where does it go? You might think it goes straight to the blockchain, but nope. Instead, it enters this kind of chaotic global waiting room.
This waiting room is called the mempool. It's essentially a holding zone, a staging area for all the unconfirmed transactions. Again, if you're thinking in database terms, it's like a space for uncommitted transactions. But here's the thing, not just any transaction can get in. It has to pass a bunch of checks first.
You can think of every node on the network as a bouncer at a club. Before it lets your transaction into its mempool, it runs through a whole checklist. Is it formatted right? Is the signature valid? Do you actually have the funds? It's making sure you're not trying to spend the same money twice. This is super important because it stops the whole system from getting clogged up with spam or fraud. Okay, so our transaction is sitting in the mempool, it's passed the checks. Now, how does it actually get picked and put into a block? Well, this is where the miners step in, and a massive competition begins to solve a really complex mathematical puzzle.
The security of the entire blockchain really hinges on this one concept, a cryptographic hash function. Think of it like a machine that takes any data you give it, in this case, transaction data, and spits out a unique, fixed-length digital fingerprint. It's a one-way street. You can't ever go backwards from the fingerprint to the original data.
And this right here is what makes it so powerful. It's called the avalanche effect. Just look at this. We changed one single letter from a lowercase r to an uppercase R and boom, the output hash is completely different. It's totally unpredictable. And that property is absolutely crucial for the puzzle miners are trying to solve.
So what is this puzzle? Well, miners have to find a hash for their block of transactions that starts with a certain number of leading zeros. The only way they can change the hash is by changing the input data. And the one piece of data they're allowed to change is this little arbitrary number called a nonce, which just stands for number used once.
And this whole process is what we call proof of work. It is a brute force race. Miners grab transactions, add a nonce, hash it, and check the result. Does it have enough zeros? No. Okay, change the nonce, hash it again. They do this over and over, literally trillions of times per second across the network, until one lucky miner finds a winning hash.
Okay, so a miner has found the solution. They've won the race. But how does the rest of the network actually agree that this is the correct new block? Are we just supposed to take their word for it?
Absolutely not. And this is so important. One miner can't just add a block all by themselves. The entire network of thousands of nodes has to reach a consensus. They have to collectively agree. This solves a classic problem in computer science called the Byzantine generals problem, which is basically, how do you get a group to agree on a single truth when you can't fully trust anyone?
So, the winning miner broadcasts their new block and the winning nonce to everyone. And here's the beautiful part. While it was incredibly hard to find that nonce, it's super easy for everyone else to verify it. The other nodes just take the block data, add the winning nonce, hash it once, and see if it works. If it does, and all the transactions inside are still valid, they add the block to their copy of the chain. It's like a decentralized commit protocol.
The block is now on the chain, which means our transaction is officially in the ledger. So, is the journey over? Well, not quite. It's there, but now it needs to be solidified. It needs to become immortal.
This is where the idea of confirmations comes in. See, every new block that gets added on top of the block containing your transaction is counted as one confirmation. You can think of each new block as another layer of digital cement being poured on top, making it harder and harder to ever change.
So how many layers of cement do you need? Well, there's no official rule, but the industry standard for a transaction to be considered truly secure and irreversible is about 6 confirmations. After 6 blocks have been built on top of yours, the cost to go back and try to alter it becomes just astronomically high.
And this is the secret to what makes the ledger immutable. Because each block is cryptographically linked to the one before it, changing just one thing in our old transaction would mean an attacker would have to remine not just that block, but all 6 blocks that came after it, and they'd have to do it faster than the rest of the entire network. It's a practically impossible task.
So there you have it. From a simple click in your wallet to a permanent, immutable record on a global ledger. It's an incredible system for creating trust without needing to trust anyone. But it does make you think, right? What are the trade-offs? What's the cost of all this immense computational security?
Thanks so much for joining us for this explainer. If you found it helpful, we'd love it if you'd like, share, and subscribe for more deep dives. We'll see you next time.